Let's take a look at an example of conditional probability. When two events, B and A, are separated by a vertical bar, that is read B given A. And as we'll see, when we're trying to calculate the probability of B given A, we want to restrict ourselves to only looking at outcomes in which A has occurred. So the problem says, a certain college requires a 2-course sequence where the courses have to be taken in order and nobody can take the second course without first passing that first one. So below, a Venn diagram is drawn for you, and it gives us some numbers with it. 60% of students who take the first course will pass it. And of those who pass the first, 75% will pass the second. So that last part is a conditional probability. The statistic that's given is only based on those who passed the first. It doesn't include those who didn't pass the first. So first, let's try to fill out our Venn diagram with as much information as we can so that we totally understand the situation. Now, what's the population of interest here? It would be students who took that first course. We don't want to consider students in the college who didn't take that first course. So we want 100% of our data to be contained within that outer bubble. And now we have to decide where our data goes, though. First of all, let's define the bubbles, A and B. It says that A represents a student passing the first course. So not everybody who takes the first is going to pass it, only some will. And those who do will go in the A bubble. That means that those who don't would go in this outer ring. They failed the first. Okay. Now, we want 60% of our data to be inside bubble A. And one technique I use for keeping it straight in my mind is I'll label the boundary with the 60%, which means I don't yet know exactly where the different people will be placed, but I know that I need 60% in that bubble somewhere. And then there's one more event, B. That's a student passing the second course. That would be the very inner bubble. Okay, so what does it mean to be in the inner bubble? You passed both. What does it mean to be in that middle ring? Well, you passed the first, but failed the second. Maybe not failed, but for some reason didn't take or didn't pass. The second. All right, so now I think we understand what the different areas represent. And the problem says for us to place dots into the different regions to represent the percentage of our population that falls in these categories. So first of all, how many dots in all do we need? It says let a dot represent 5% of the data. So if you take your 100% and divide it by 5% per dot, you get a total of 20 dots. And this is what we need to distribute within our diagram. So how many of the dots would have successfully completed the first course? To find that, you'd want to take 60% of the 20 dots. That'll give you 12. So I know that I need 12 dots somewhere inside bubble A. How many dots would go outside bubble A then? Well, 40% of the dots. That would be 8. So I'm going to write that in, that I need 40% in this region. Now notice I didn't put the 40 on the boundary. I actually put it in the region itself. So to me, what that means is that the 40% is just in this region here. And people inside bubble A and B are not part of that 40%. There we go. We got 8 dots. All right, now the last piece of this is to figure out how to distribute the remaining 12 dots. What portion of them go in the inner bubble and which ones go in the middle ring. And this is where the conditional probability will come into play. So, conditional probability says, of those who passed the first, 75% passed the second. So I want to go and multiply my 0.75 times something. But what do you multiply by? All the people? Or just those in bubble A? The answer is you do it times just those in bubble A. Because that's what the conditional probability is based on. It's based on those in bubble A. It's not based on everybody. So 75% of A makes it to B. That's going to be 9 dots. So let's go ahead and place 9 dots here. All right, how many dots does that leave in the middle ring? 3. And now the diagram's complete. So we can use our diagram now to find probabilities. And notice that these probabilities are not conditional probabilities. So that means that all their denominators are going to be out of the entire population of 20 dots. Conditional probabilities restrict the denominator to just a portion of the overall population, as we'll see. But these are the type that we had done before. So let's find the probability of just A. All we're looking for is outcomes which are favorable to A, meaning they are successes for passing the first course. That would be anybody inside the A bubble. It could be these people and these people. They're all inside the A bubble. So what numerator do we need here? 12. And that was actually one of the givens. They said that of the population, 60% will pass the first. All right, now let's look at just bubble B. So we don't want this anymore, and we don't want that. We want to find anybody who's a success for B, meaning they passed the second course. Anybody in this bubble. our numerator will be 9. But remember, it's still out of the total population. You're basically asking, if we pick a random dot out of all the 20 dots, what's the chance of that dot being in bubble B? It's 9 out of 20, which happens to be a number that wasn't given directly. It's 45% chance of any given student being in bubble B. Now let's find the probability of A and B. Well, the interesting thing here is those who are a success for B are also a success for A. So these are people who are in A and B. And so it's still 9 successes. 45%. And now let's find the probability of A or B. Oops, lost one of my dots. So for that, we can expand our bubble. The middle people will definitely count because they're in both A and B. And even these people will count too. They're in A but not B. But they should be counted. So it's 12, which is 60%. And, interesting to note that the A or B bubble is the A bubble here. Okay, cool. So now let's look at the conditional probability. There are 2 formulas for it. I'm going to start with this top formula first. If you want to find the probability of B given A from a diagram like this, you should divide those outcomes that are favorable to both A and B by those outcomes that are just favorable to the restriction A. So let's take that one step at a time here. We're looking for outcomes favorable to A on the bottom. We're looking for favorable to A and B. That needs to go on the top. So, how many are favorable to just A? 12. 12 people passed the first course. How many of those are favorable to both A and B? That's the middle bubble. 9. So what is the probability of B given A? 75%. This was actually given in the problem. So what does B given A mean here in the context of the problem? It's the probability that a student passed the second, given that they passed the first. Probability of B given A. So it's 9 out of 12. There is another formula that we can use to get that same answer. And it's really helpful if you know the probabilities of A and B and the probability of A. We can just plug them in, and that'll give us the conditional probability as well. So you put the probability of A and B on top, which we had already calculated earlier, which was 45%. And then you have to divide by the probability of A, which was 60%. And if you do that, you again get 75%. All right, what if we reverse it? Does the order matter? Can we find the probability of A given B? It turns out order does matter. So this time, we're not going to restrict ourselves to just looking at bubble A. In this case, we are going to look at only bubble B. Because the second part of the conditional probability is the condition, is the restriction. So when we write probability of A given B, then B is the restriction. That's what you look at as your like your new sample space. Okay, now we need those that are favorable to A and B on top, divided by those that are just favorable to B. Okay, well, we know that there are 9 dots in the B bubble. How many of them passed both the first and second course? All of them. You can't pass the second without passing the first. So it was actually 100%.